Yeah. Yes, Andy,
Yes.
ma'am. Yeah. So am
Uh,
I audible properly, right?
Hello, sir.
Yeah, am I
Yes,
audible
sir, you're
properly?
audible, sir.
Yes, yes. Let me give you your intro, sir. Thank you. Hello.
Yeah, yes, sir.
Yes. Good evening, ladies and gentlemen. My name is Dr. Arun Kumar from CSC Department, Vardhaman College of Engineering. I welcome today's session of our short-term training program. We are honored to introduce Mr. Brajesh Kumar, our esteemed resource person for this event. Brajesh Kumar brings over a decade of rich experience in research, analytics, and software development to our table. His expertise in analytical and statistical skills have been pivotal in identifying and capitalizing on opportunities for the efficient quality across global entities in manufacturing, distribution, and retail. As a product insight manager at ServiceNow, Mr. Brajesh Kumar professional journey is remarked by a significant stints at JDA Software, TCS, and Union Bank of India, where he excelled in the roles that demanded high levels of analytical rigor and strategic insight. An alumnus of Indian Institute of Management, Indore, with an MBA in Business Strategy, and Birla Institute of Technology, MISA, with BE, also certified with R Software Professional from IIT Hyderabad. Mr. Brijesh Kumar representative experience include being world-class business and data analyst at JDA Hyderabad, where he was instrumental in developing and implementing process for global value delivery team. His focus was always been on solving complex business problems using data-driven methodology and engaging CXO level discussions to map business cases. He was also contributed and published on a white paper on green supply chain and distributive supply chain management in developed nation. As we proceed today with this today's session, we are look forward for his insights and knowledge that Mr. Brajesh Kumar will share us and drawing from vast reservoir of experience and research. Please join me in welcoming Mr. Brajesh Kumar.
Yeah. Thank you, Arun sir. It was well summarized. I thought that I will give a brief introduction, but you completed everything. So thanks for that,
You
Arun
can
sir.
continue.
Yeah. So, I will start directly. I will not take much time here. So can I get the access so that I can share my screen? And
Yes, sir, you can share your screen, sir.
okay. Give me a moment. So you can see my screen, right, everyone?
Yes, sir.
Yes, sir, we can see.
Perfect. Let's start the session. First of all, I would like to thank Vardhaman College of Engineering for giving me such opportunity where I can share my experience and what is happening in the industry that I can bring on the table here. And thank you, Santi ma'am, for connecting me with this 5 days program. And I hope this session will be useful. And even we know that it's very short, but yes, it will give you an overview that how the market is going to be changed in future and what are happening in terms of the IoT and federated machine learning. So today, what I'm going to do that I'm going to present this federated machine learning for IoT, that is Internet of Things, networks. And so, as you know, this in this digital age, IoT has become integral part of our life. We know that how everywhere machine learning and federated learning are getting used. A lot of data is getting collected, and we can start from our homes. Now we are using Alexa and different wearable devices. Earlier it was simple watch, but now we are using smartwatch in different companies, different format and all. But yes, those all are IoTs, and what we are doing that we are rapidly expanding this and so generating a vast amount of data. So there are two ways. One is like the collection and one is like uses. We are using this smart watches, smart thing in our houses, offices, and even public spaces. So first we are using those devices and then we are collecting the data and again analyzing and upgrading all those devices. So it's like completing a cycle. And with this data, like how we are handling and processing this data, that is a big challenge. And that's where this topic, federated machine learning, comes into play. We already aware that our general machine learning, where we are just collecting the data, analyzing it, and based on that, we are making different decisions. But in what is happening in federated machine learning, how it comes in our life, and how much changes it is making, let's dive in. So, with that, what we are going to do, this is the agenda for today's discussion. So, first, I will give a brief introduction that what is federated machine learning and its history. What are the techniques we use in FML? What are the applications like where we can use this and how we can see the data is making changes or not? What are the approaches which are getting adopted while using this FML model? Obviously, challenges will be there because we know we are dealing with a lot of data. And we will take one example, a use case, which we will discuss that how we can implement and how it can be benefit. We are not going to touch the coding part, but we are going to touch the basic where we will understand what is happening in FML with IoT. So as you already I hope in the last 3 days, you already gone through this federated learning. So we are not going much time to spend on that. And our focus today is going to how we can apply federated learning on IoT devices, that is Internet of Things devices. So we can recap what happening in FML. So we know that this is an approach to train and operating machine learning models and in distributed manner. So what we are meaning here that we have local files, we have local machines where we are asking the system to learn individually. All are independently. It's not like that data are coming and they are learning from each other. It's like independently they are learning. And these data which we are giving the system to train, it is kept locally on those individual devices or servers. These models are getting trained and updating itself in terms of collaboration without sharing the raw data. So what we are doing that we are doing like we have data, we are not, we have big, if we have 4 different houses and there are different devices. So we are asking each device to learn by itself, make model and all, and then we are aggregating at one level. So here in the picture, we can see that what we are doing that local files are there. We are receiving and giving data. Data is getting downloaded and then data is getting uploaded at the central level when the system is already running and making its model and it's working in iterative process, improving and optimization by time. And then we are doing the model averaging where we are taking the best model and then choosing that. So here we are saving our time. We are asking the model to learn and there is data privacy. So in FML, what is happening, each device or server performs their local model training using its own data and they periodically shares only the models update, not the data. And with the central server, or we call it aggregator. What this central server does, the central server combines the model which got updated from multiple devices and it creates a global model that captures the knowledge from all participants, which we are talking about servers, and while preventing that, while keeping the data intact, like privacy and security maintenance there. So This is the basic we already aware in the last 2-3 sessions. Now coming to my next part where like we are talking about Internet of Things, that is like a buzzword. Everyone is talking about IoT. So what is happening in IoT? So IoT, it refers to the network of physical devices or vehicles, appliances, and other objects wherever a sensor is embedded, a software is there, and connectivity is there. And what we are doing that we are enabling all these physical devices to collect and exchange data over the internet. And these devices are typically equipped with sensor, as we know, and actuators also. This allows them to interact with the physical world and communicate with each other, as well as the other system also and applications. So what IoT is doing, IoT enables a seamless integrations of all the physical objects into the digital world and creating an intelligent system that can monitor, control, or whatnot, like optimizing the various process and services. And it has applications. When we talk about IoT, a lot of applications are there in different sectors like smart homes. We're talking about nowadays smart homes, smart cities, healthcare, agriculture, transportation, and manufacturing. Everywhere, everywhere IoT is getting used heavily. Nowadays, like individual people, like their home are completely smart homes, like with in their hand, with the mobile they are using, they can control the complete appliances in their house from TV to refrigerator to whatnot. So that is like we are talking about the IoT. And one example, like we now heard about autonomous vehicles. Like if you talk about a vehicle which is collecting a lot of data based on different parameters, and these are, and if we count this data, then this automation vehicle like per day or is there 4,000 GB data of getting collected. This report was generated by Intel, and we have multiple sensors like cameras are there, how much data is collected per second, radar is there, our sonar system is there, GPS signal is there, so leader is there. We know that if we are using a smart car, a lot of functions are there. First, with our system, whatever the command we are giving, it is learning from that, and then it is giving us back based on that. Suppose when I drive my car, and if I leave my home and wherever the destination it is, if I start from that destination place, then the first option, if I search the Google map, I will get my home address. And that is how the model is learning. Like it knows that the person is not at his home. So obviously the first option will be his home. Without asking, the map is giving my home. If I want to go some other place, then definitely I have to change it. But by default, it is giving my home address because it knows that from my home, wherever I'm going, I will return back. So that's how the car system is collecting data. A lot of data is there, and companies are expanding all those information to improve the data car model. Now, we know that if we have system, then obviously challenges will be there, and we call it IoT network challenges. So the Internet of Things and related technology which we are talking about, obviously they plays a pivotal role in designing, controlling, and managing the large and complex system, such as industrial process automation and optimization. Also surveillance in smart lighting, parking, waste management, leakage management, digital, smart grid, and many such industries, such places we are using. So when we talk about the typical architecture of this system, which often consists of various homogeneous and distributed interconnected devices. We already talked about this terminology, distributed, and they are interconnected. So what happened in traditional machine learning setting? The data which got generated by IoT devices, it is getting collected and analyzed at the central node. It's not distributed, such as physical server or cloud cluster, which usually have powerful computational resources. But when we're talking about IoT devices and in this our distributed function, that These are usually deployed at diverse geographical location with limited control. And IoT devices are very resource constrained, as we know, and suffer connectivity issues due to low bandwidth. So heterogeneity in hardware and software. So communication are also a common challenge for any of the IoT infrastructure if you're talking about. So considering the above challenges which we are discussing, let's define it more and let's check that how it is changing our thing. Additionally, IoT devices can require highly personalized data that needs to be protected. So we have to make sure that compliance is important. And from the context of IoT, like federated machine learning is a decentralized. When we talk about not IoT, not federated generic machine learning, then it's not decentralized. It's centralized, as we discussed now. So this is decentralized approach to machine learning where like multiple devices train models in collaboration. But the point is that they are not sharing the data with a central server, or we can call it cloud in more clear term. So instead of the models are trained locally on the devices themselves, enhancing the privacy also and reducing data transmission overweight. So obviously, if we are avoiding the data transmission, then our performance will go up. So now what are the challenges here? We know that. So first one is the limited bandwidth. In IoT devices, what happens that they often operate with a limited bandwidth, primarily due to their small size or might be low power consumption. And these are the constraints which restrict the amount of data that can be transferred and processed that is important for efficient data compression and communication protocol. So that is limited bandwidth. The next one is power constraint. Like most of the IoT devices, when we talk about, they operate on limited power sources, such as battery or energy harvester. And these constraints require IoT networks to optimize the power consumption at every level, including the data processing, when we're talking data processing, communication, and device management. So obviously power constraint is there. The next one is data privacy concern. So IoT network deals with vast amount of data, and these are sensitive data which we collect from various sources. Like if I'm talking about Alexa only, it's very small device in our home. But we might heard sometimes that Alexa is giving some suggestion or some, it is making prediction, which obviously something which was secret for us, for our family, and like it is learning everything, whatever we are doing, whatever we are talking, and based on that, it is doing. So obviously data privacy constraint is there. And this data, it can include our personal, environmental, and organizational information if we talk about the larger part. So ensuring data privacy and security becomes a significant concern, and steps must be taken to secure these communication channels, like encrypt data and ensure secure storage and processing. And the last one, need for distribution. So what does it mean? Like IoT network generate enormous amount of data, and it is often impractical to send all this data to a centralized servers for processing and analyzing. So distributed techniques, it allows us, as we discussed, that it allows us to reduce the need for a large scale data transfer, which will minimize the latency and enhance the privacy. Now the model which we are talking about, that is federated model, federated machine learning model. So in this is the like entry of federated machine learning. It faces challenges which we discussed, and all the challenges we discussed like limited bandwidth, power constraint, data privacy. So to overcome all these challenges, FL technique, what it does that it enable efficient and secure processing and analyzing of data on IoT devices. And federated learning tactical involves a lot of training machine learning models on distributed IoT devices. These models can be trained collaboratively and share updates with a central in this figure, you can see that like edge service there, cloud is there. So starting with our global model download, when we are talking about global model download, then well, our model is like when we are getting data. With the data, we are receiving the data from different IoT gateways, like our car, mobiles are there, smartwatch is there. And with that, we are doing local training at that individual devices, that is like distribution. From that, we are doing model compression. And with this, we are updating our model each time we are running and we are uploading that. Then this will go to the server, which is like where we are, every system is working and they are doing the decompression. What the compression happened for our different training model and all, it will decompress, and then finally it will do model aggregation. When we are talking about model aggregation, it means that it will take the best model based on the information provided, and then we will get the result. So as we mentioned that to mitigate all those issues we just discussed, like we are talking about now, edge computing. So this edge computing, let me come to the next slide. So what is happening in edge computing? So we call it edge AI, and in edge AI, like it protects our local and user data and allow the ownership. So it is talking about privacy and communication both. In edge AI, what is happening? That edge refers to the device or system that are locally that are the edge of the network. So edge of the network, like in our house, if we have different corners, just simple as example, we have different devices at different corner, and we are calling it edge because these are different devices, and these are typically closer to the source of the data generation. Edge AI involves running artificial intelligence because AI is there and it processes the data directly on these edge devices. It is not working centrally, and we are not relying on centralized cloud computing. So the main idea behind Edge AI is to bring AI capabilities closer to where the data is generated and processed and consumed. So this has several, obviously we are working at distributed levels. Obviously there will be several advantages such as like reducing latency, enabling our real-time decision making, improving privacy and security, and reducing the need for constant internet connectivity, because the model is working at the base level, at the edge. And edge AI can be used in various applications like smart homes, industrial automation, surveillance system, autonomous vehicles, and also these are wearable devices, which are very common nowadays. So by processing this data locally on edge devices, AI models can provide us immediate insights and responses, which will enable a faster and more efficient operations. And that what it will do, that will implicate in the standard FL problem, which will involve the learning of globally shared statistical model from data that is residing on the potentially tens to thousands of remote devices. This model is trained under the constraint that the data generated on the edge devices, which we kept at the locally, and periodically updates are happening, communication is happening to the central server, and since the data is not shared at any point, the privacy is preserved. Privacy is very important here because we know that a lot of machine learning, federated machine learning, everything is happening. Banking system, they use a lot of these models to run to predict that which customer will buy credit card, which customer will be defaulter and all. And in that, privacy is very important. It's like make or break for their business. If this model runs properly, they will get good return, good churn out will be there. But if not, then it's difficult for bank to operate. And also it can be risk also if the model is failing and data privacy is not working. So privacy should be preserved. And other benefits, like it also reduces the communication overhead in IoT network, as it is only sharing the periodical model, right? And it updates in there only instead of sending huge chunks of raw data to the server. So now we discussed that. Now we can check that what are the applications of this federated machine learning in IoT network. So let us discuss that how FML can be applied in IoT networks. So FML can be applied in IoT networks to facilitate the collaborative training of machine learning models using this different technique. Like first is when we are talking about that how FML can be implemented, then these are the process. Like first one is the data collection. So IoT devices collect the data. We can see that the data is getting collected from their respective environment, wherever the edge is there. And this could be sensor data, a user behavior data, or any other relevant data which we can collect. The next one is the local model training. You can see the number here, the number where we can say that how we are modeling our training. So each IoT device which are locally trains a machine learning model using their own data that they have collected. So this local model is trained using traditional method like either we call it gradient descent or stochastic gradient descent. So these are the model which they train. Then they do the model aggregation. Model aggregation means the local model already be collected from different IoT devices. They send to the central server or aggregator. And this server aggregate these all local models and creates the global model. After that, what we do that we do model distribution. So the central server, what it does that it distributes the global model to the IoT devices in the network, and each of the device receives an updated version of the global model. So it learned locally, then it aggregated it, sent back to the model, and again updating the model. So what we are doing that by different iteration, we are just improving our model so that we can predict the better result or we can just give the better result. That is our end goal, right? So that's why we are doing this model distribution and local model update. And after that, what we are doing that the IoT devices using this, whatever the global model update happened, they are using that model with their local data. And they perform model updates using techniques like transfer learning or fine tuning. Finally, we are doing the model aggregation again. Why? Because the updated model from the IoT devices are sent back to central server for aggregation. And this process of aggregation and distribution continues. It always learn from what it did in the past so that it will reach, it will give minimum error when they predict something. When someone asks some question, the answer which we get, it will be very close to 100% correct. And that's the iteration process happen. Then the privacy, obviously we are talking about privacy, the privacy preserving technique will be there, like FML incorporates various privacy preserving techniques to ensure that the privacy of these IoT devices should be maintained. This can involve techniques like different privacy, data anonymization, or secure multiple party computation. Then what we do that model evaluation. Obviously, we made a model, so evaluation will happen. So the performance of this global model, which is evaluated periodically to access its accuracy and generalizability. So if necessary, further iteration of model updates and aggregation performed to improve the model. So it's continuous iteration where like we are trying to achieve better result each time, and that the continuous iteration happens. Now coming to the architects, this is very important. Once we'll understand it, it will be very easy that how the FML model works. So the architect is like the architect of FML in IoT consists of basically three layers. Edge layer, which you can see at the down, where the devices are there. Then the fog nodes are there, and then core is there. We call it cloud. So in the edge layer, each layer has its specific role in the overall FML system when we aggregate all these. So in edge layer, what happens? The edge layer consists of edge devices. You can see cameras, wearable, car, whatnot. And then these edge layers, whatever the data we are collecting and processing this data locally only at that device only, allowing for our real-time decision making and reducing the latency. And in the context of when we talk about FML, edge devices also participate in the training and in inference of machine learning models. These edge devices can perform pre-processing and also feature extraction from raw sensor data, which enable them to send only relevant information to the higher layer. So what edge layers are doing that they are collecting data, running it, getting the result, and whatever the relevant information is there. So when we collect data, a lot of just junk values are there. So we have to massage the data. So model is doing all those things by itself. So reducing the noise and whatever the relevant data or models should go upward, only that is getting passed. So yeah. The next layer, so that is at edge level where then the next layer is fog layer. In fog layer, what is happening? As we know that when we talk about fog, it's between the surface and the above. So the fog layer is an intermediate layer between the edge and the cloud layers, and it consists of different fog nodes like receiver and all computing. So this fog nodes are more powerful computational devices when you're talking about, and they can perform more complex tasks compared to the edge devices. And these nodes also collect data from multiple edge devices and perform the aggregation. They filter it and it is additionally they perform before forwarding to the data to the cloud layer the way edge was doing. And the fog layer is also responsible for reducing the network congestion and also filtering out the redundant or irrelevant data before sending to the cloud layer. So in FML, fog nodes can also participate in training machine learning models in a distributed model and then collaborating with other nodes in fog layer. The next one is cloud layer, which is above that. So the cloud layer is at top and cloud layer is the centralized layer, which we talked about earlier also. And this is responsible for aggregation of all this data which is coming, processing it from multiple edge on fog devices. So it consists of basically cloud servers or data centers that have computational power and storage capacity for execution of their resource intensive machine learning tasks. What are they do? What kind of tasks? Like the cloud layer perform tasks such as model training, model updates, and higher level of decision making based on the aggregated data. So after collecting all the data, obviously it will update the models, first train it, then update it, and then based on that, it will make decision, whatever the aggregated data came. So the trained machine learning models are then deployed to the edge. So we discussed that how it is moving from bottom to up, and then again after uh, doing the massaging of the data and giving the better model, it will again pass it to the lower level. And this is help in real-time decision making closer to the data sets. So the cloud layer also facilitate secure communication and coordination among different edge and fog devices by providing how they're doing it by providing authentication, encryption, and access control mechanism. So basically what we are doing here, the architect, when we are talking about the IoT, so it leverages the distributed computing capabilities of edges, fog, and cloud layers. And by offload, how it is doing by offloading all the computation and decision making to edge and fog layer. So it is not doing the basic work, but yes, it is at level up where it is doing just processing, reducing latency, and increasing the scalability. But at the same time, the cloud layer provides the necessary computational resources and coordination to the training machine learning models and making it higher level decision. So what are the role of
Sorry to interrupt you, sir. We just wanted to take one peek with all participants and with due respect with you, sir. So could you please switch on your camera?
Sure.
Yeah, participants, please, you are requested to switch on your cameras and already permission is given. Soumya ma'am, please take the screenshots.
Sir, can you stop sharing the screen for a while, sir?
Sure, sure, sure.
Yes, sir. So that like.
Soumya ma'am, is it done? Can we start, restart the session? Yes, sir. You can continue, sir. Thank you so much, sir.
Thank you, Santi ma'am. So where were we? Yeah, we were discussing about the role. So role of each layer in the FL process. So in the federated learning process, what is happening that each layer had its own significance and they plays a specific role. So when we talk about edge, so edge layer has it is responsible for collecting the data as we know and pre-processing the data from local devices or sensor there only. It also performs local model training on the edge devices using the collected data. And the edge layer also handles local interference, allowing the edge devices to make it real-time prediction without relying on cloud resources. And by training and interfering locally, the edge layer has preserved data privacy as raw data doesn't need to send to the cloud. So that's the role. When we talk about the fog layer acts as an intermediary because it's between the cloud and the edge, and it provides additional computing resources and services. It also performs data aggregation from multiple edge devices, which collects data and reduce the amount of data that needs to be transmitted to the cloud layer. So in intermediate, it is just allowing the data which is important. At edge, we get a lot of data which might be just noise, not important for making any decision. But the fog layer has its importance. It is allowing only those data which are important, and that only needs to be transmitted to the cloud layer. And then fog layer also, they can perform further pre-processing the data and feature extraction and filtering of the data from edge devices as we discussed. And what will happen that it will definitely improve the quality and reduce the noise. Then fog layer also participate in the model training process by collaborating with other fog or edge devices. So it allows the distributed training and improved model accuracy. Now coming to the topmost where we talk about the cloud layer. The cloud layer serves as the central hub for FL learning, where global model training and aggregation takes place. It receives model updates from edges and fog devices, as we know. It aggregates all this data and then trains a global model using all this aggregated data. The cloud layer facilitates the coordination and synchronization of model updates from multiple devices. And it also participates in the federated learning process. So what happens that after the training, the global model, this cloud layer again distribute the updated model to the edge and fog layers. And then it helps in inference and deployment. And at higher level, it is doing the analytics work. It extracts all the insights from all the aggregated data, and it makes decisions based on all these learned model. So the edge layer focuses on local data collection, pre-processing, and model training, whereas the fog layer assists in data aggregation and distributed model training. And then cloud layer serves as the central hub. So this layered approach in federated learning enables intelligent decision making. And what they are doing on top of that, they are maintaining the privacy and also reducing the need for centralized data storage. This is the role of layers. Now we talk about the different models. When we talk about different models, like which all kind of models are there. So in that, we use algorithm. Obviously, when we are talking about models, so algorithm will come. We all are from CS background, and algorithm is important for building a model. So there are certain algorithms which are used in this IoT, FML IoT. So first is federated averaging. So what happening that in IoT networks that can use different federated machine learning algorithm to achieve collaborative and distributed learning method across different devices. And this algorithm enable devices to train the model locally on their data and then integrate to the model updates from the multiple devices to create a global data. So in the picture here, you can see that different local models are there, different ages are there. You can see that these IoT devices at different age, local model is happening. Then all these models are going upward, aggregation is happening, and then their model aggregation, the global model is coming. So to tackle this federated network, where how big is it and there can be challenges. Google first, they formulated the very first vanilla federated algorithm and they called it Fed average, FED Fed average. So, but however, this Fed average doesn't account for the intrinsic heterogeneous nature of federated network because there are many algorithms that developed to balance the global model, which performance include stochastic based algorithm and primal dual optimization. These are the different algorithms, and a significant effort has been put into developing a robust, fair, fault tolerant, and heterogeneity aware solution. And with that, this federated averaging model came in the picture. And we know that this algorithm involves here different ages are there, different local models are there, and this aggregator model collects the data, works there, then it's sent to the server for aggregation and updates by averaging all the parameters at the local models. And this aggregated model is then again sent back to the devices for further training, and process is repeated until a convergence is happened. So this is federated averaging model. The next one is federated stochastic gradient descent. This is very interesting. Like in this algorithm, what happened that each device performs local training using a stochastic gradient descendant of its own data. Like what is happening here? Like this stochastic gradient descendant takes a different approach than the previous one. So instead of using the entire data set, what it does that it randomly selects a single data point or a small batch of data, we can say that. And then it computes the gradient, and that gradient, with that they update the parameters. So this randomness, which introduces noise into the overall optimization process, it helps in the local minima and converge it faster. So as the formula, you can see that SSE is there. So in that, it's like here the parameter are like vector is there, that how much iteration will happen at I. Alpha is the learning curve. Then we have also this loss function because we are talking about where the convergence is open. So we have learning curve. We are talking about learning rate also. Like learning rate, it is like learning rate. We know that it's the critical hyperparameter in this stochastic gradient descendant, and this learning rate only determines the size of the steps. When we are talking about optimization, that how much size of the step will be taken in this optimization process. So if we are setting it very high, then the algorithm might be overshoot the minimum value. But if you are setting it low value, then it might result in slow conversions. So this method is used widely when we training the deep neural networks we are doing and other machine learning models due to efficiency, especially when we are dealing with the large data set. But the problem is that it may require tuning of hyperparameter such as learning rate or optimal performance. So this is STD. The next one is secure aggregation method. So this algorithm where we are talking about privacy and security. And how we are doing that? We are using cryptographic techniques. Like local models are getting encrypted before sending them to the central server. The central server then gets this encrypted data. They perform the aggregation operations on these encrypted models and then send back again to the encrypted global model only. And then these small devices, which we are users, age and all, they can decrypt the global model and continue training. So this is how it works. So local model training, it encryption, aggregation, decryption, everything is happen in repetition. And this is how we are getting a secure model where privacy and security is cryptographic. Now the next one is federated evolutionary learning. So what is happening here? This algorithm generally what they do that they combines federated learning with evolutionary algorithm. So each device, when we are talking about each device, like sensor is there, they evolves its own population of model based on the local data. And then they give the best model based on that from each devices and they send to the central server. Central server, what does that? It combines them using evolutionary operators like either mutation or crossover. And then what is happening? Then the resulting global model is then sent back to the device for further training. So every time the evolution is happening and the model is getting trained. Then we have federated reinforcement learning. In this algorithm, what is happening, how the model works, the algorithm combines all the federated learning with the reinforcements learning. And each device collects its own data and perform their local training using reinforcement learning technique. The local models which we are talking about, they send back to a central server, which aggregates using techniques like Q-value averaging. And this aggregated model, again, it's sent back to the devices for further tracking. And training is going on again. So overall, this algorithm enables IoT devices to collaboratively learn and improve their machine learning model, at the same time preserving the data and security. They also leverage the distributed nature of IoT networks to achieve efficiency and scalable machine learning. So when we talk about scalability, what does we mean it? Like in our FML addresses, scalability, we do it like we are using distributed computation and parallel training across distributed edge. We have different edges, so parallel training is happening on distributed edge devices. So instead of traditional centralized approach where all data is collected first and then processed at the central level, here FML distributes all the computation and training process across multiple edge devices. And instead of sending all the raw data, which we know that it will not go to the central server for training, the training process is happening on the edge device. And this allows for localized computation and reduce the need for heavy data transfer to the centralized server. When we are utilizing this computational power of multiple edge devices, FML can handle a large amount of data and perform training in parallel. So one of the benefits of the FML is its ability to scale with an increasing number of edge devices. We can increase multiple devices. As more devices we are joining, obviously the federated learning network is coming, the distributed computation and parallel training happening. So all these capabilities of FML allows for allows for a seamless scalability. And each new device, when they are getting added, they contribute its computational power to train the process, making the overall training faster and more efficient. So overall, FML benefits from different edge devices in terms of hardware capabilities, because we can easily add more edges and the data distributions. So different devices may have different processing power, right? When we talk about at the start that they are of different nature, their data characteristics are different, and they are allowing a more representative and robust model. The federated learning framework, it can adapt and utilize the specific capabilities of each device. Thus, so ultimately, it is benefiting from the increasing number of edge devices. So this is scalability we talked about. Now, when we're talking about a use case, so first of all, when we are talking about federated machine learning and a model, obviously the use case should be defined with the objective. Like when we talk about a smart city, like IoT applications with algorithms to design an end-to-end federated machine learning system for smart cities IoT applications. And in IoT, smart cities, traffic management is there. We have air quality control, public safety solution, smart parking, smart lighting, smart waste collection. With these IoT's devices, we can make a city smart. And we have to take here various steps which need to be followed. Like here is the process, whatever we discussed in the before slide. So first of all, define the problem. This is the outline that how you will build a model. First, define the problem. Identify a specific problem or the use case you want to address anywhere in the smart cities of IoT application. For example, like you want to predict the traffic congestion, or what you want to do that energy uses. How is the wastage is getting utilized, public safety monitoring and all. That is how you have to define the problem first. After that, start collecting the data. Like you have to determine the data source available in the smart cities, like sensors are there, cameras are there, a lot of other devices are there. First, collect the data and pre-process the data. Ensure that its quality and integrity should be maintained, and we are pre-processing the data properly. Then we have federated learning architecture, which we discussed 2 slides back. Like design a federated architecture, and that allows multiple devices or edge nodes to collaborate and train machine learning models. Determine the structure in that architecture. Determine the structure of nodes, such as like it will be central server, edge, device, or cloud-based component will be there. Then our algorithm selection. We discussed all those algorithms. We have to choose what is our need, how our problem statement which we defined. Based on that, choose an appropriate machine learning algorithm. And the data, we have to see that what is the data characteristics. Consider the algorithm which you are choosing. It's suitable for a centralized training also, such as federated averaging, sequential aggregation, and differential privacy technique. Then the step 4 is our model creation and initialization. What we are doing here, we are developing a machine learning model and the architecture that will fit our problem statement. And also it will incorporate the privacy preserving mechanism. Initialize these model parameters on central server and distribute the model to all the edge devices. Now we already distributed the model. Now what will happen? The training process will start. So implement federated training algorithms that will allow our edge devices to train the model using their local data. And also at the same time preserving the privacy. Also define our communication protocol. That is important, that how the data is exchanging the model updates and aggregating them on the central server. So that communication we have to define in the training process. Then the step 7 is model aggregation and evaluation. Here, what we are doing that we are aggregating all the local updates from edge devices, which we have connected to the center server using either federated average or other aggregation techniques. Then evaluate the performance, how it is doing of this aggregated model using relevant metrics. Obviously, like if you want to measure the accuracy, the precision, the recall, the energy consumptions, like that. Then once your model aggregation and evaluation will done, you have to deploy it and give the inference. So deploy this aggregated model back to the edge devices after model aggregation and everything. And deploying the aggregated model back, what we're doing that we are also giving this cloud services for inference in real-time scenarios. They will predict, they will make decision based on the deployed model. Then the step 9 is model monitoring and maintenance. So we have to continuously monitor that how it is doing, how is the performance is doing when we deploy this model. We have to collect the feedback from edge devices or the end users who are using this. And time by time, periodically, we have to retain or update the model to adapt the changing conditions or data characteristics. How sometimes we know that after certain time, the data characteristic change. The data which we are getting, it is updating. And the way it is making decision based on that, we have to periodically update our model. Then the step 9 is important where we have to talk about security and privacy measure, because when we talk about robust system, we have to also implement a security mechanism like encryption we already discussed, or access control, who can access our model, and also the data anonymization we have to do, ensure the data is confidentiality and their integrity has been maintained. Then incorporate all these privacy preserving techniques such as federated learning, differential privacy, or secure aggregation to protect our user privacy. Once we are done, then we have to think about scalability and optimization. What we are doing here, that when our model is running fine, we maintain everything, performance, security, everything, then we have to scale it, design the system which can handle a large number of data, because when we are keep adding the edge devices, we have to maintain the efficiency and effectively we have to distribute the computational workload. So we have to think that each model is working and each edge device is there, but we have to maintain that how the consumption is happening for that. Then the last one is integration and interoperability, where we are maintaining that seamless integration is happening with the existing IoT platform or the frameworks which we have developed in this smart cities application. Establish one interoperability standards, like you have to define it to enable collaboration between different vendors or stakeholders. After that, also we have to maintain that continuous improvement is happening. Continuous consider means like you have to take the feedback, how is the system performance is of. Sometimes what happens that when I run the model, the performance was doing very bad. Then we reiterated, performance improved. Then certain kind of data started getting added from different devices, and again it reduced the performance. So continuous check should be there. Continuous just check the feedback, how is the performance happening, what is the user requirement. Sometimes user request came at the start and after some time it changes. So we have to think about that. We have to incorporate all those user requirements to improve our federated machine learning system over time. So once we are following all these steps, right, what we are doing, we are able to design and also implement an end-to-end federated machine learning system for smart cities where IoT applications are there. And how it will benefit us, it will enable collaboration, scalability, privacy, real-time decision based on the decentralized data source. All those things we can do. These are the benefits of our steps when we are doing a use case on smart cities. Now challenges, what can be challenged? Because when we are talking about smart cities, then obviously challenges will be there, right? So challenge is heterogeneity. What does it mean that when IoT system consists of devices, like these devices are with having different hardware capability, right? All these appliances are different. Someone mobile is different, wearable are different, cameras are different. All these IoT system have different hardware capabilities. We call it system heterogeneity, and it generates massive amount of data in a highly disparate manner, like statistical heterogeneity will be there. While the effects of heterogeneity are long studied and already proven in IoT networks, there have been many attempts to mitigate the problem. Like these methods cannot fully handle the scale of federated networks, and heterogeneity itself, it's in IoT network, like when it refers to the diversity of devices like data types, network condition, they can have negative impact on our federated machine learning model. And these few unique challenges, like most noteworthy, is like training over largely heterogeneous data samples. We have a lot of data samples from heterogeneous devices, and we are doing the training. These models are too complex, and they highly influence the training process and make our traditional federated machine learning unsuitable to be directly deployed. So in that case, we have to take care of that, and how we can manage those all those negative impact which are coming in our model. So model and data personalization should be there. The first one is model and data personalization. Like what we are doing, that we can leverage techniques like how we are transferring the data, what is the model personalization that can adapt to the model to the specific characteristic of each IoT devices. So what will happen that if the model identify that what is the characteristic of that device, it will allows for a better performance, even in the presence of heterogeneity. Because we are our building our model says that based on the hardware characteristic or device is learning from that. They are better performing based on that. Then also adaptive learning algorithm. So when we talk about adaptive, it's like FML algorithm, we can design it to adapt and adjust their learning rates. We discussed about learning and how the model is learning based on the heterogeneity of these IoT networks. What will happen? This will help us in achieving a balance between how we are exploiting the local data on each device and aggregating knowledge from different devices at the same time. And it is adapting learning from there. Then we have differential privacy and data aggregation. What we are doing in differential privacy, we have to preserve the privacy of sensitive data on IoT devices. So that FML incorporates techniques like federated averaging and secure aggregation, the model which we talked about. And these models ensure that aggregated model is calculated without, without exposing our individual device data. So what will happen if we are not exposing, then obviously we are overcoming our heterogeneity in terms of privacy concern. Then communication efficient protocols. We have to make it very clear that the heterogeneity is there in IoT networks. Then that can result in differences in different devices, their capabilities and computational power. And also the network connectivity, we know that it's different. So our FML algorithm, it can be designed to account for these differences and use a communication efficient protocols. What will happen that it will optimize the communication between our devices and the central server. So we are just reducing our impact of heterogeneity. And the final one is dynamic device selection. So what happens that some FML approaches consider selecting a subset of devices in each round of training. So they are not directly selecting the devices, but subset of devices and doing in a small training with the preferences have given to like what are the small characteristics of the device or which are the better performance of that device. What will happen with this? It helps to minimize the negative impact of devices with extreme or outlier. We know that there are some outliers data in the network. It will remove that, and the impact, negative impact which will happen in device, it will just minimize that. So these techniques and consideration which we're talking about, this illustrates how federated machine learning can handle the negative impact of heterogeneity in IoT networks. What will do it? It will allow for effective and privacy preserving collaborative learning. So IoT networks are heterogeneous. We know that in real life scenario, when we are this federated learning model are deployed over an IoT network with different data sets, different device capabilities, data availability, network quality is different, battery levels of each devices, like some phones remain on for 7 days, some phone just get drained in 1 day or 2 days. So the capabilities of all these power backup are different. So we have to think about that on that. And when we are doing that, heterogeneity will be there, the impact will be there, but we know that we are breaking it down. And briefly, we already breaking it down, the data that one by one is learning, the model is taking it in step by step, and we are reducing the negative impact on that. So we will discuss that how we can do that in the next when we how we are handling the statistical heterogeneity. Here we can see that in distributed optimization problems, what generally happens that in when we are making an assumption, the data is independent and identically distributed, but that is not happening. In IoT devices, you can see that it generates and collect data at high dependent and inconsistent fashion. There are no any consistency in the data. The number of data points also varies significantly across different devices, and which adds complexity to the problem modeling when we are doing. Also, the solution formulation analysis we are doing. After the analysis, we have to do the optimization. But these devices, when we are talking about this, could be distributed in association with each other, and there might be an underlying statistical structure which can capture all these relationship, how statistical structure relationship is there. And with this, their aim of the learning is like single globally shared model. Statistical heterogeneity makes it difficult to achieve an optimal performance. So that we have to take care. Now that is statistical. Now we have to think about the system heterogeneity. So in system heterogeneity, it's like very like of IoT devices in a network. We have different underlying hardware. Like hardware, like when I talk about hardware, it's CPU, the memory, and these devices might also operate on different battery levels and use different communication protocol, Wi-Fi, LTE, etc. So in conclusion, what I'm telling that the computational storage and communication capabilities differ from each device for each device in the network. But IoT networks have to cope up with all this struggle as well. So like low level IoT devices operate on low battery power and bandwidth and can become unavailable at any given time, right? So this we have system level characteristic that can introduce and many challenges. It can introduce many challenges when we are training our models over the edge. One example we can simply take like federated network consists of hundreds of thousands of low-level IoT devices, but only a handful of active devices might take part in the training. Not many data which are coming from different, it can be noise. So in such situation can make trained models based towards the converge towards the active devices. But also low participation can result in a low convergence time, right? We are not taking all the devices, but low participation is happening, and the convergence will be low. The timing convergence time will be low when we are doing the training. So due to these reasons mentioned here, which we discussed, so heterogeneity is one of the main challenge when we are building a model on federated IoT networks and federated algorithms. So there recently one study is it was happening and it claimed that it addressed the challenge of heterogeneity. Therefore, in this paper, what they were discussing that they how they are doing the empirical analysis for evaluating the existing approaches and quantifying their effectiveness in mitigating the problem of integrating. So this is how we are making our solution with system heterogeneity. Now coming to the benefits, which is the federated machine learning of benefits, how we are getting benefit. So let's explore this, that how we are employing it. The first one is privacy protection. Everywhere in, I think every now and then in our slides, we talk about privacy protection. When data is there, privacy is the first criteria. So we know that with the increasing concern over data privacy, predicted machine learning ensures that it is sensitive data remains to the local devices. And this eliminates the need to transfer the data to a central server. If the data is not transferring, it is reducing the risk of data breach or privacy violation. The next one is efficient data processing. Very clear. We have like a lot of data is there, a massive amount of data is there, but by implementing FML, the resources required for data transmission and storage are significantly minimized here because all the data are locally at the edge only. And this approach allows us for localized processing and reducing the strain on network bandwidth. So it is also covering the network bandwidth also. Now, improved model accuracy. We know that by collaborating training of all these models on multiple devices, it will enhance our model accuracy and generability. Each device, we know that it is learning from its local data, capturing unique patterns and contributing to the overall model's performance. And the model is running based on that. Then it is decentralized infrastructure. In federated machine learning, we are eliminating all the need for a centralized infrastructure, so making it suitable for all the IoT networks with limited connectivity. Local devices can autonomously train the models, be it at the edge or with the device itself. It is giving us real-time decision making and reducing dependency on a central server. So this decentralized infrastructure helping us in performance, security, and also the model is learning, making real-time decision. Then we have scalability. Obviously, when we are done with our modeling, when we retain our model, so it allows us for easy scalability as a new device are added. Whenever a new device added, it's easily it can be scalable in IoT network. And each new device, it can contribute its local knowledge, further improving the overall model performance. So it's like a lot of friends are meeting from different backgrounds, sharing their knowledge, and everyone is getting benefited, and a common knowledge is getting built. In that way, we can think. So yeah. So this is what we learned in summary. Like in federated machine learning, we know that it offers decentralized, privacy-preserving, efficient approach, which is processing and analyzing vast amount of IoT data. It ensures our data privacy, our model accuracy, it improves, it enables us in real-time decision making, and these are helping us in our future decision making, how we can perform, how we can make our better life with utilizing all these IoT devices. Now, that's all from my side. Thank you, everyone. Yes. Santi ma'am, Arun sir.
Yes, sir. Yes, sir. Participants, if you have any questions, you can ask, sir. I think, sir, we have some questions in chat box.
Okay.
Sir, someone is asking, like, sir, a little elaborate on local model training and at fog level model training process.
So, ma'am, when we discussed about local means you are talking about age, right? So,
So, yes, sir, please.
am I audible, right?
Yes, sir, you're audible, sir.
Yeah. So I was saying that local means age and fog is, so there are three layers which we discussed at the start. So when we're talking about age, that is like the device, our device. Device means it can be our mobile phone, it can be wearable, and it can be anywhere. Physically, we are collecting the data based on sensor and all. But when we are talking about fog layer, it is a layer up. So at this level, all the information which we are getting from different edge level devices, they are getting aggregated. From if I'm using a smartwatch, a lot of data is getting collected. Uh, how many steps I took, what is my heart rate, and means sleeping hours, everything. And this data might be if I want to check my health, might be my steps. If I'm taking 10,000 steps a day, might be not important for my health risk in future. So what will happening in our fog layer? It is giving us all the related information and making a model based on that. First model with my data at the smartwatch, where it is collecting data directly, heart rate, steps, everything. But at the fog layer, it is not sending all the data, but all the data which is relevant to my health. Might be 10,000 steps is not sufficient. So what is this data is important? No. How is my heart rate? How is my O2 rate, the oxygen rate and all. So that is important for my health. So a layer of data already got stopped at the local place. At the fog level, only 50% or 40% data got transferred, and that data is relevant. So now more refined data came for the future prediction. After that, once the fog layer did its work, it will send the more relevant data to the cloud, where it will take only suppose heart rate, and based on that, it will make prediction that how is my health? Am I at the risk of any disease or not? So that is how we can differentiate that different layer. Chat.
Anyone else? If you have any questions, you can ask.
One person asked about stochastic mean. So you want to understand that, right? So as you mentioned, right, what exactly here? This is also helped us in understanding our that take one point. We have different data sets at every place. We are not going to take all the data there. What we are doing here that uh, we are using a small data set, not the whole. It's like a small batch of data points we are taking, and we are using that to compute a gradient. Gradient means like a slant, and we are updating the parameter and removing all the noise in this optimization process. So how you do that? You have taken one point and then calculated, predicted some value, and you have prediction training set, and you have the actual training set data. You take the difference, the delta value, and then again, what is the different delta came? Suppose it's some value came. Again, the model is reiterating with the other data points, other small batch size, and then the next delta value it will get. Is this data value is lesser than the previous one? If it's yes, then yes, we are going at the right direction. And in the same way, we will get the best model where it is cost effective. Cost effective means that the minimizing our local and converging faster towards our goal. So that is our stochastic gradient model is there. And in that, certain parameters are very important when we're talking parameters like vector is there, that at how much at iteration we will happen in our formula. We have to give that how much iteration it will happen. Learning rate is there, that what is the step size in the parameter in that space. Also the loss function, that we have to choose data points on that, how much loss we can think that. And uh, what we're doing, that we should not either, it should be not very less, it should not overshoot the minimum, and also it should not make our model slow. So with that, we have to take care of the stochastic gradient data model. Santi ma'am?
Yes, sir. Yes, sir. Just a minute, sir. Arun, sir, are you there?
Yes, ma'am.
Yeah, please, sir.
I would like to extend my heartfelt gratitude for the insightful session you conducted on federated machine learning for IoT, bridging the gap between edge and the cloud. Your expertise in the field and the depth of your knowledge made the session incredibly valuable and engaging. The way you explained the complexities of integrating IoT in a federated environment and the practical implications for bridging the edge and the cloud technologies was truly enlightening. Your presentation not only provided us deeper understanding about the subject, but also sparked innovative ideas for applying these concepts. Your willingness to share your experience and insights is greatly appreciated. The information you have been presented has been significant contribution to our understanding of the evolving landscape of technology in this area. I once again thank for your valuable time and providing such a beneficial learning experience. We look forward to the possibility of having you as in the future. Professor Dr. Shanti Makamam is invited. She'll be providing a brief on tomorrow's session.
Thank you so much, Arun, sir.
Thank you, ma'am.
For giving wonderful introduction of Brajesh, sir. And Brajesh, sir, it's very happy to know that your educational background is also from BIT Mishra.
Yes,
Uh,
ma'am.
Yes, sir. Yes, sir. I'm very happy to know. And we are very happy to have you as a speaker, sir. And thank you once again for sharing your valuable knowledge with us. And dear participants, tomorrow we have Mr. Arpit Yadav from Analytics India magazine, and he will be enlightening us with fostering innovation through federated machine learning, balancing technological advancements with privacy assurance and impact assessment and road ahead. And tomorrow we also have a valedictory session from 8 to 8:30 p.m. Then after the validity session, you have to appear for the assessment, and which will be conducted from 8:30 to 9 p.m. And we will be releasing all of your certificates as per the eligibility criteria within the 10 days of completion of this STTP. And dear participants, thank you for attending STTP, and we appreciate your contributions and hope that you found this event to be a valuable learning experience. Thank you all. Good night. Thank you so much,
Excuse me,
Brajesh
ma'am.
sir, once again.
Excuse me,
Thank you,
ma'am.
Santi ma'am.
Thank you, sir.
Hello, excuse me, ma'am.
Yes, sir. Yes, sir.